right, so this is the second lecture dealing with Gibbs and Gibbs free energy concept. Okay, so we left off with this nice reaction showing the relationship, how both enthalpy and entropy can be involved in this system. All right. Excuse me. Goodness gracious. There are two methods of figuring out delta G. One is you can calculate the delta H using calorimetry. You remember that. Hess's law, the nice tables that you guys did. Or the enthalpy of formation values, which you get from that attached thermodynamic quantities. You just look up those values, take the products minus the reactants, and then you just calculate delta S using the entropy values, same thing, and then you could calculate delta G using the whole equation. Okay, so that's what we're going to do first with this. Given this exothermic reaction, but entropy-wise, it is showing a negative value. So is the reaction thermodynamically favored? It's not going to jump right out at you. Now remember I had said that delta S is going to be given in joules. So make sure you fix that when you're doing the problem. But what you can do now is simply plug that into the Gibbs free energy equation. So hit the pause and see how you can do. Well, welcome back. Hopefully you wrote out the equation and remember to write the signs in. That's super important when you're doing this, because you're subtracting a negative. All right, so this is just, you're doing the temperature right here, and this, of course, you have to divide by 1,000 to make it kilojoules. And when you punch those numbers in, that was large enough number, because you're subtracting a negative, to actually make delta G positive. Okay, now in doing this problem, you've got to make sure you put the plus sign, like when you take the AP test, to show that that is a non-T FP. All right. So anyway, that positive value means it's not going to be thermodynamically favored. So that's a pretty straightforward way of doing these problems. Okay. Now, this second example we'll walk you through together. At what temperature does the previous reaction become thermodynamically favored? Assume that delta H and delta S do not change as temperature changes. Okay? So the way you can do that is the point when it becomes not thermodynamically favored, the cutoff point, obviously, between negative and positive, is 0. So you can set this whole thing equal to 0. And when you do that, then you can rearrange, get T all by itself, and when you rearrange that, it's delta H over delta S. And then you can just divide them, and you'll end up with a temperature. And in this case, 285 degrees Kelvin is the point where it would become thermodynamically favored. Okay, that would be enough energy to drive the system forward. If you get a negative Kelvin value, you know you did something wrong. Okay, so this is a nice little circle this little equation. You can derive it, but really, if you just enthalpy divided by entropy will give you the value there. Okay. This slide deserves a circle and stars again, so circle the whole slide and stars, you can predict, like for a multiple choice question, whether it's thermodynamically favored by using this chart. And I'd also like you to write in your notes there, memorize for AP exam. This will really help you with these types of questions. If you can just remember that delta H negative, with this one being positive, both of those are the way things should be, if you want to look at it that way. And that, of course, it would be thermodynamically favored process at all temperatures. Okay? We just had an example where this was negative and negative, and thermodynamically favored process at low temperatures, but if the temperature sneaks up there a little bit, then they become not thermodynamically favored. And so just make sure that you know these relationships. I think just a memorization of this chart is the way to go. So make a note to yourself there to memorize those things. All right, so here you have delta H being negative and delta S being positive for this reaction. So if we go back to the chart, you've got this right there, and that is positive. So if you know those things, you're not going to have to crunch any numbers. You just go, yep, delta H is less than 0, and delta S is greater than 0, so it's thermodynamically favored at all temperatures. So you can see how much time that would save you on a question instead of trying to do some calculations. So that little table is a really good one to know. All right, now, second, you can calculate delta G using the change in Gibbs free energy of formation at standard conditions, and that would be in your attached thermodynamic packets. Remember, we had the delta H, we had the delta S on there. So guess what the equation is going to look like? Just like it is on your purple sheet. You're going to write this out, and you're going to crunch those numbers. Now, what I'm going to have you do today is actually solve these problems using your numbers on the attached thermodynamic quantities. Again, we showed you yesterday how the numbers vary. Okay? So, this should look very familiar to you. So if you were going to do this problem right here and crunch these numbers, you would do the products and then minus the reactants. So go ahead and do that using the delta G values that are posted. And they'll be a little bit different than the ones that I'm going to show you the answer for. So pause and crunch those numbers. Okay, so coming back here, I told you to skip that step and always jump right to just plugging the numbers in. Obviously, yours is going to be the same here. So for solids in their normal state, they're going to have a value of 0. I honestly don't know how much your numbers varied, but should be right in that wheelhouse there of a negative 1582, which of course is the value for the aluminum oxide. So then you're going to go 2 times the quantity 0. Don't forget to put the mole amounts in there. I forgot to emphasize that yesterday. Even though in this case they're not going to affect anything because this was the value for the aluminum is going to have a value of 0 because it's